Thank you for the introduction. Yeah, I'm Morgan, and I study ozone pollution in Nova Scotia. I'm in my last couple months of my Master's of Applied Science degree at St. Mary's University, and my supervisor is Dr. Aldona Wycheck. So ozone is a secondary pollutant. It's not emitted by anything. It's produced.
Loves it.
It's produced in the troposphere from reactions of nitrogen oxides and volatile organic compounds in the presence of sunlight. And ozone is a very strong oxidant. It can oxidize lung tissue, plant matter, and building materials. So we want to keep levels of ozone as low as we possibly can. There's lots of different sources of ozone's two precursors in Nova Scotia. So for NOx, the green pie chart here shows the biggest NOx sources, and mobile sources is the majority. And for VOCs, the biggest source is natural sources, but the biggest anthropogenic source is also mobile sources. So to limit ozone production, we have to keep these two precursors as low as possible. So the data for my project is all taken from the National Air Pollutant Surveillance Program, and they have 10 stations across Nova Scotia, which you can see in the map there. And my study period is from 2000 to 2018, so I use hourly ozone, hourly NOx, and a 24-hour average VOC that's measured once every 6 days. And I just want to keep in mind that the Halifax station was moved halfway through 2017, but I use data from the old station for 2017. And then the new location is actually further away from, it was on Barrington Street, which is heavily impacted by vehicle traffic and had very high NOx emissions there, but it was moved to a street around the corner, so it's less impacted by NOx emissions now. So that's just something to keep in mind, and I'll point that out as we go through. And these stations are managed by Nova Scotia Environment and Environment and Climate Change Canada. And the Nova Scotia Environment puts out great summary air zone reports every year that summarizes how each air zone that's shown on the map there is doing in terms of our national standards, which are called the Canadian Ambient Air Quality Standards, or CAQS. So for our ozone, we've actually had deteriorating air quality or increasing CAQS values in 3 of the 4 air zones in the last few years. And the Western air zone is very close to exceeding our CAQS standard. The standard is 62 parts per billion of ozone for 2020, and that's going down to 60 parts per billion for 2025. So if we don't decrease our CAQS values in the Western air zone, we will likely exceed our national standards in the coming years. And then the only other data source I'm using and for this presentation is the air pollutant emissions inventory for the NOx and VOCs. And that's an estimate of all source and non-point source pollution across the province. So it includes transportation. So this is a plot of hourly ozone in Halifax by year. And I also put the Nova Scotia air quality regulation on there, which is 82 parts per billion for 1 hour ozone concentration. And we've only passed that 3 times over my study period, and the last time was in 2002. So we don't actually exceed any national or provincial standards in Halifax, but and our 99th percentile ozone has decreased over this period, but 75th percentile median and 25th percentile ozone is rising over this period. And you can see just from this plot that in the last three years of data, 2016 to 2018, there is an observable increase in ozone in Halifax. So to help explain these trends, I wanted to look at trends of ozone's 2 precursors to see if we can find out why there has been deteriorating air quality at some of the station locations and why ozone is increasing in Halifax. So these are NOx emissions and concentration trends over the study period. And we can see that both emissions in orange and concentrations in black are consistently decreasing over the period. And then because I saw an observed change from 2012 to 2018, I redid linear regressions for these for the more recent period, and I found that the slopes have changed in that more recent period. So the emissions decreased by a factor of 2 from 2012 to 2018. So they're slowing down. And we don't see the same thing for NOx concentration. It stayed about the same for that more recent period. But I did mention the station change in Halifax to an area less impacted by NOx emissions. So I'm assuming that lower NOx value for 2018 is actually because of the station change, and I'm not sure what it would be if the station had stayed in the same location. So the other precursor is VOCs, and I did the same thing for VOCs, and I found similar trends. So we see a consistent decrease in VOC concentrations over the years in green, but then for the more recent 2012 to 2018 period, we see a slowdown in concentrations reductions, and the same thing for our VOC emissions, where we have a decrease, a significant decrease for the full period, but for the shorter period, we're actually seeing effectively no change because the standard error is bigger than the slope. So it's basically leveled off. And our emissions reductions are slowing down in recent years. And another reason I did this for the 2012 to 2018 period is there's a lot of literature coming out of the states showing the same thing, where while they expected consistent decreases over the last 20 years, we've actually seen a leveling off or a slowing down of these emissions reductions in recent years. So because I know we do receive some pollution from the states, I wanted to know if our own emission sectors were actually increasing, or if this was because we're receiving more pollution from the states. So I looked into emissions by sectors from the APEI. And for VOCs, we can see the 3 largest sectors, which are commercial, residential, institutional, paints and solvents, and transportation, are actually rising in the last 7 years. So and pretty significantly. And then for NOx, while we don't see a rise in recent years, we still have decreasing trends from 2012 to 2018. You can observe a leveling off in those trends. That is definitely a different trend than for the full time period. And actually in the most recent 3 years, 2016 to 2018, NOx transportation emissions are rising. But we still do have like a net decrease of these emissions over the full time period. So I wanted to see how these net decreases have affected different processes of ozone formation in Halifax. So I looked at something a lot of us know well, which is titration in the downtown Halifax station. So I compared 2 different periods. The older period is 2006 to 2011, and the newer period is 2012 to 2017. So what titration is it's when ozone levels fall at the source of freshly emitted NOx. So NOx is very high at the source, like it was on Barrington Street during morning and afternoon rush hours, and ozone is actually titrated so ozone levels fall. And this is shown well in this plot, where we have a peak in the solid lines, which are NOx, during the morning, in the afternoon, and a subsequent dip in the dashed lines, which are ozone. And the peak is very high in the morning, and it's a little bit lower in the afternoon, and the ozone dip in the afternoon is a lot shallower too, and that's just because pollutants, the NOx isn't, well, one of the reasons is because the NOx doesn't build up as rapidly, it's dispersed more readily, so not as much titration occurs. But between these 2 time periods, 2006 to 2011, 2012 to 2017, we've had a decrease of 20 parts per billion of NOx from this morning rush hour, and that's due to our emissions decreases. This resulted in a small increase in ozone. So we're decreasing the dominant precursor, but we have an increase in ozone. And this happens in a lot of urban areas when that are heavily saturated by NOx. This has happened all over the world, where we see decreases in NOx, but we're actually seeing a rebounding effect in the ozone because it's not being titrated as much anymore. So a better or a more accurate way to look at total ozone without this titration effect is to look at something called total ozone. So the titration effect is only temporary. So as this air mass actually moves away from the source of NOx, we are getting a net production of ozone once again. So total ozone is ozone plus an estimate of the amount of ozone that has been titrated through the titration reaction. And we get that estimate through this equation at the bottom here, which is ozone plus NO2 that has undergone the titration reaction. And then we subtract primary NO2 emissions, which is estimated as 10% of freshly emitted NOx. So essentially, ozone plus the amount of ozone that has been titrated is total ozone. And I have total ozone on here as the dashed and crossed lines. So total ozone decreased with decreasing NOx by 1.7 parts per billion between the two time periods, which is more like what we want to see with decreasing NOx emissions. And for a long time, a lot of the questions we've been asking are, how far does this titration bubble extend from the downtown core? Does titration happen at the suburban station of Lake Major, which is only 12 kilometers from our downtown Halifax station? So I repeated the same analysis for Halifax at Lake Major, and I found that NOx concentrations are 10 times lower at Lake Major, and the peak in NOx is actually offset an hour from the peak in NOx at Halifax, which is consistent with the time it would take to transport NOx from Halifax to Lake Major. So we see the peak in morning rush hour NOx around between 9 and 10 a.m. So NOx is being transported to Lake Major. And the amount of ozone that's been titrated is basically the difference between ozone, so the dashed line, and total ozone, which is the dashed and crossed line. So we can see in that earlier period that there was actually 5 to 7 parts per billion of ozone being titrated throughout each hour of the day, which is interesting because we thought that titration was only happening right at the source of emissions. But in fact, there is titration occurring at Lake Major. And for the more recent period, NOx is very low. It's between 1 to 2 parts per billion, the bottom solid line there. And the difference between the dashed blue line and the dashed and crossed blue line is it's a lot smaller. It's only about 1 to 3 parts per billion. That was on average titrated in the more recent period. So there's less titration happening now, but there's still a little bit. And also something to note is that both ozone and total ozone have increased between these two periods. So while we saw a decrease in total ozone at Halifax with NOx reductions, we're seeing an increase in total ozone at Lake Major, even though the NOx, the solid lines, have decreased from the two periods. So why is this happening? Well, I believe it's at least partially related to ozone production efficiency. So this plot here shows the instantaneous rate of ozone production. Each of the curved lines is a rate of ozone production in parts per billion per hour. So on the far left-hand side, we have 1 parts per billion per hour all the way up to 30, which is the smallest curved line. And then on the y-axis, we have NOx concentrations, and then the x-axis is VOC concentrations. So if you ignore the black lines and look at the red arrow here, if we were to decrease NOx from 50 to 5 parts per billion, we're actually increasing the rate of ozone production from 1 parts per billion an hour to 5 parts per billion an hour. And this is because ozone production is always more efficient at low NOx concentrations. And I believe that's what has happened at Lake Major. Okay, and I just have one more thing to talk about. This was a highlight from my research project. So I looked at transported ozone pollution across my study period. And I used top monthly quartile ozone in Halifax, so the most elevated days in Halifax from each month. And this took away the bias of the springtime maximum that we have in Nova Scotia. And I used the idea that if there was elevated ozone at every single station across Nova Scotia, this had to be due to pollution that's been transported from elsewhere, because many of these stations are rural and remote and don't have any local sources. So if we take the case of June 11th, 2015, we can see the daily maximum ozone at all stations in the yellow circles that are the station locations. And then the percent change from the monthly mean is beside those station locations. So for example, the stations in the western zone, which are known to be heavily impacted by transboundary pollution, are have the highest changes from their monthly mean on the day of high ozone in Halifax. So to back this up, I did a high split back trajectory and found that it was pretty straightforward that we had transport coming from the northeastern United States. So I did this for all of the top monthly quartile ozone days in Halifax. That was 1,444 days. And I created an algorithm to look at spatial correlation across the province on all of these days. And the criteria with which I diagnosed a transported ozone event, it's changed as this project has developed, but for the purposes of this presentation, at one point I did classify 157 days as transported ozone. And these are a subset of days that we are still confident are transport, but it's only 11% of the total elevated days. And for each of these 157 days, I ran 72-hour backwards trajectories that end in Halifax on the day of the peak. And this map is a composite plot of the trajectories and the frequency with which the trajectory ran through each grid cell. So we can see that the majority of the frequency of trajectories pass through the northeastern United States and the southwestern Ontario and southern Quebec, which is what we have for a long time suspected using some episodic studies, but we've never known this for sure. So a deeper look at the days that weren't classified as transport with some of my favorite meteorologists at Environment Canada showed that there's actually indication of transport in the days that weren't classified as transport. So that made us realize that this algorithm is extremely underestimating the amount of transport days. So I've refined the algorithm since I did up this map, and I found a better estimate of total transported pollution to Nova Scotia is between 19 and 63% transport. 19% still follows a very stringent criteria. So I would guess it's a lot closer to 63% transport. Yeah, so my conclusions, we see ozone is rising at Halifax in recent years. And we're not sure why, but it could be due to increasing emissions in several sectors. Lake Major appears to be within the NOx titration bubble of downtown Halifax, and total ozone is increasing at Lake Major due to decreasing NOx emissions because of production efficiency. And although it is very difficult to determine how many ozone days were produced by transport, my best lower estimate is 19%, and I am pretty confident that it's closer to about 60%. And our dominant source region is the northeastern USA and southern Ontario. And while that's all interesting, our own anthropogenic VOC emissions are rising, and we do have the ability to regulate that or have some control over that. So I think that should be the focus for Nova Scotia going forward for air quality improvement. And yeah, I'd just like to acknowledge my research group. This is a very outdated photo. And then Al Wilson and Lucy Chisholm as well for helping me out this semester. And I'll take questions.